Yeah, good afternoon and welcome to the Cryosphere Pavilion. My name is Christina and I'm a geophysicist at the University of British Columbia in Vancouver. And I would like to introduce our next session. The session is entitled New Budgets Confirm Permafrost Region is Already Warming the Climate. We will have 4 speakers and our first speaker will be Gustav Hegelius from Stockholm University. Please welcome our first speaker.
So, thank you very much for that introduction, and welcome everyone. Let's see if I'm getting... Sorry, the slide thing. There you go. Okay, so I'm the first speaker in the session, but you'll hear from all of these 4 people. So the last session we talked a lot about like broad scale overarching permafrost projections, looking further into the future, and you often hear about the long-term impacts of permafrost. And we do want to emphasize the sort of slow onset, but also like the really long-term effects of permafrost. But there are actually also rapid processes and permafrost are happening already. And here we're actually focusing on the changes that we're already seeing and the current greenhouse gas budgets from these areas that we see are actually already affecting climate. So the first talk this will be a summary of a paper that just came out a few weeks ago. It's from a project called Recap 2. I'll get more into this soon. So the Recap 2 permafrost region greenhouse gas budget and the possibility to reconcile top-down and bottom-up methods. I'm presenting this on behalf of a very large amount of co-authors that we'll see in a slide coming up later on. I want to start with putting us in the context of the global carbon budget in this. This is the global CO2 budget. We'll actually be discussing several greenhouse gases in this talk, but for here I'm using the global CO2 budget. This is from the paper that just came out last week, announced here at COP, and this shows you have the year at the x-axis and then the gigatons of CO2 at the y-axis, and it shows the growth of, and the top part, the emissions that we're doing, fossil carbon, land use change carbon, so emissions into the atmosphere. And at the lower end, you see where these emissions are ending up. So you have the ocean sink, the land sink, and the atmosphere. So you can see from here that roughly half of the CO2 that's emitted is taken up again by the natural ecosystems. Half of it ends up in the atmosphere, the light blue, a quarter roughly in the land sink, roughly a quarter in the ocean sink. And I think this is a very good slide, a very good perspective to have in mind, but I also want to emphasize that now we're talking about the terrestrial permafrost systems, the land permafrost systems. Where we are in this big grand scheme of things, we are in the land sink, or actually what we're seeing, the processes that we're studying, they will lead to a sort of a smaller land sink. So the sink of the land will be smaller and smaller and smaller due to the processes that we're studying. We talked about the Boreal forest and other things in the last session, and we're going to keep talking about that now. But that's just for context. And of course, we're studying the permafrost system because we're concerned with thaw accelerating global warming. So this is a simplified scheme of the permafrost carbon feedback. Global warming thaws permafrost. You see a very dramatic example here from the Canadian coastline. You have a person there for scale. And this leads to greenhouse gas release as organic matter decays. The permafrost region stores twice as much carbon as in the atmosphere, 3 times as much carbon as in all living vegetation on Earth. And if even just a fraction of that is released as greenhouse gases, that's a big problem for the global climate. And there are additionally a lot of direct impacts to the permafrost system, to ecosystems, to infrastructure, and humans. And we actually have a session dedicated to those direct impacts on the ground starting at 4 o'clock today, if you're interested in that. So this image shows you, this is from the European Space Agency CCI permafrost project. This shows a perspective not of where permafrost is currently thawing, but actually where it is warming the most rapidly. So you'll see more about this later. But I want to emphasize that in the far north, where the permafrost is still, where the ground is still largely quite cold and there's extensive continuous permafrost, the rate of warming is the highest. So along the Siberian coast, etc. And this drives a lot of surface processes and a lot of actually increases of greenhouse gas emissions happening also there, even though it's still permafrost further down. Surface processes and the abrupt thaw leads us to actually have quite large emissions also in the continuous permafrost regions. So the study that I'm presenting here is multi-year work that's gone into this. You see the long co-author list here. It came out in Global Biochemical Cycles recently. And it's a greenhouse gas budget for the terrestrial permafrost regions for the past 2 decades, 2000 2020. And as you see in the title, we include CO2, methane, and nitrous oxide in this budget. So it's really the first comprehensive budget that summarizes all 3 of these greenhouse gases for this region. But first, I want to back up a little bit and talk about RECAP 2, which is the project under which we did this assessment. So it stands for Regional Carbon Cycle Assessment and Processes. RECAP 2. It's coordinated by the Global Carbon Project, so the same organization that publishes the global CO2 budget, global methane budget, global nitrous oxide budget. So this work is coordinated and will be more coordinated into the global budgets to really make sure that there are regional budgets that feed into the global budgets to improve the accuracy of the budgets moving forward. So it's a Global Carbon Project with funding support from the European Space Agency. This work. And the aim is to produce regional greenhouse gas budget for the past 2 decades based on the best available data and models. So we don't use all models or all data. We use the models that we think that we have good reason to think work best. So there have been systematic tests and assessments of models, and we use the one that we think really work. So synthesize, harmonize, and compare budgets. And I'm presenting the permafrost region, but this is actually done for the whole world. So 14 regions of the globe, scale and compare between regions. And here you see the RECAP 2 regions where budgets are being made. We have the sort of pinkish permafrost region in the top that cuts across several regions. But actually there is a separate budget, either has been published or being published for all of the other regions as well. Most of the other regions are based on traditional geographic boundaries rather than sort of defined as the permafrost region cuts across. And I also actually want to emphasize that there's also a RECAP 2 oceans. So the same amount of work is going into doing budget for all of the ocean basins as well. So this is a large project with a lot of exciting science coming out that it can really inform global policy and give us the best available budgets for these regions. But back to the permafrost region. So this is the extent that we have worked with. The bright colors is the regions that we included. So this is the Arctic Boreal permafrost region that we worked in. So you see some gray areas, and they are actually not included in this budget. So the sort of steppe biome at the Tibetan Plateau is not included here. We only work with the Arctic and the Boreal zones, mainly due to the fact that we had better data availability there. So hopefully for next time around, we'll be able to include the full permafrost region. And this is just a slide this slide is to emphasize that we're working in a massive area, but we have also massive local scale variability. So the size of the permafrost region, it's roughly 3 times the European Union, 4 times the European Union. It's very, very large. But even at, we have meter scale variability. And if you look at the scale of, I like this image because it's from the area where I did my PhD work many years ago. You see 1 kilometer there on the lower side for scale. But I just want to emphasize the wealth of different ecosystem types and landform types that we have within a region such as this. And there's a lot of different things going on in this image that I don't need to get into. But all over the permafrost region, the variability is a mess. And one corner of the permafrost region is very different from another corner, which is one of the challenges we have. Large area, large variability, not that much data. So it's a challenging problem. And we attack this problem with 2 distinct perspectives, the bottom-up budgets and the top-down budgets, and we try to get them to agree. Spoilers that we didn't quite make it, but we made some progress. But the bottom-up perspective is basically data-driven and model-driven budgets informed by observations on the ground, flux towers, chambers, and models, and then using land cover data, satellite data, to upscale and make budgets of all the greenhouse gases. And this is then contrasted to the top-down perspective from inverse modeling, which is basically measurements in the atmosphere coupled to maps of what roughly we think should be the sources of the greenhouse gases, and then using a complex transport model to try to make sense of this picture. So it's really measuring in the atmosphere versus measuring on the ground and scaling up. and getting those two very different approaches to meet in the middle, which is a large scientific challenge. You will see now, and now I'm going to go into the results. We have a lot more sort of individual results from the bottom up, because there we have a lot of different approaches and a lot more data that emerge. For the top down, for this study, we actually used the same top down budgets as was used for the global carbon project, or the global carbon budget and the global methane budget, but then we clipped out the permafrost region, and so we used global runs clipped to the permafrost region, then compared to the bottom up. But then if we start with the bottom up budgets, what do we find? So one key element to the bottom up budget is climate models, or the land surface components of Earth system models. And this is what we're seeing here. This is sort of the latest climate model ensemble CO2 budget. I know that the graphs are busy. I will get into explaining them quite soon. So these are basically the subset of, we've made a sort of informed choice of a subset of models. So this is not exactly the same models that went to IPCC. It's a subset of those models. And then we divided them a little bit further into two groups. So you see on the x-axis it says bulk carbon and layered carbon. And the models that have bulk carbon, they are the slightly simpler models that represent all of the soil just like one big box, which is very unrealistic. And the layered carbon models, they have different layers, and they are able to model permafrost more precisely. So we have two families of models here. And then you see on the left hand, you see the sort of net sum of all of the different processes. So basically the net sum of estimated CO2 budgets from these models, and they both actually show a sink of carbon taken up by this area. But it's quite sort of variable. Sink differs. The sink is bigger in the bulk carbon, slightly smaller in the layered carbon. And on the right-hand side, you see the fire emissions, which I think is interesting. You see that the slightly more developed models, they have a much higher estimated fire flux. And that's because those models actually have processes in some of them where the actual soil can burn. And those are the big, like when it burns in the Boreal forest, actually the largest carbon losses are often from the soil. It's not from the trees, it's both, of course. But having the soil burning is really key to this. But then a very important part to note here is that these models do not have lakes or wetlands in them. It says there in the title, no lakes, no wetlands. Because they are missing the lakes and the wetlands in the models, they are missing a very big part of the carbon cycle. So we'll sort of get to that in the next slide. But the models still show an uptake of CO2. But then if we go to the data-driven bottom-up upscaling, we use this land cover map that covers the whole Arctic and that is quite adapted for greenhouse gas flux scaling. And we use recent synthesis papers that have come out, a lot of different papers coming together here. So this is just the data we use to do the really data-driven, observationally-driven upscaling. You see this nice graph here shows the distribution of different wetland landscapes across the Arctic. And we're not going to get into the nitty-gritty details, but it's just to show you that this is sort of the level of detail where we try to do this upscaling of really separating the different types of lakes, the wetlands, and all of that. And at the end, we merge those map-made budgets with the models, and then we get a best bottom-up budget that shows that is summarized here. So again, quite a busy figure. You see different panels for boreal forest, inland waters, fires, wetland, and tundra. And then you have a separate line for CO2, methane, and nitrous oxide. And here a negative number means an uptake into the ecosystem. So a negative number is a sink. That is something that's good for the climate. Positive numbers, bad for the climate. So what we see is that the boreal forest, the growing forest, is still a sink. It takes up carbon. We knew that, and it's good that our models are showing that. So, but you see that the inland waters and fires, they are actually really big sources of CO2. So the inland waters and the fires alone are almost enough to offset the uptake in the growing forest. And then if we go into methane, we see that there's quite a lot of methane being released from inland waters, but then a really high numbers also for wetlands. And here it's important to remember that methane is a much stronger greenhouse gas than CO2. So here we see the weights of the different gases. I'm not going to talk so much about nitrous oxide. There's basically all of the ecosystems are weak sources, but they end up being a relatively limited climate forcing so far from the nitrous oxide. There are small points where the lot is being emitted, but overall not so high emissions. And then I can also mention on the side, you also see coastal erosion and river floods. So we also try to account for the carbon that is going laterally out into the ocean. But if we do then compare our bottom-up budget, which is here in orange, to the top-down inversions from the atmosphere, we actually see that the methods, there is some agreement, but not super good. If we start on the left, we have CO2. And here you see that the top-down atmospheric inversions, they actually show still quite a strong sink into the system, while our bottom-up integrated budget is basically neutral. So there is the largest disagreement that we have. And we think this is largely caused by, well, we think, I would guess, this is work in progress, but probably the truth is somewhere in between. Because we have reasons to believe that the top-down inversions are underestimating, because they are still missing some of the sources because they don't represent inland waters and wetlands well enough. But there might also be some exaggeration in, especially in the bottom-up budgets, we are not perhaps accounting well enough for the regrowth after fires and other processes. So there are things that we need to work on. For the methane, both methods agree that it's a source. The magnitude is different. For nitrous oxide, both methods agree that it's a source into the atmosphere. I'm not going to get into the nitty-gritty of this, but also just to show that, especially for the bottom-up budget, we also do separate it into all of the different components. If you want to dive into more of the details in the paper, you can. Separating the different bottom-up and the data-driven, the modeling, etc. So we also have a separate component for the. So this is numbers coming from the Earth system models, and this here I also again want to highlight that there's a lot of variability there, but also you know that the blue bars, which is where we have model estimates, it's very limited. So basically it shows us that the models are not able to actually estimate all of these gases and all of the processes that we want to estimate. It's only the bottom-up data-driven budget where we can actually describe all of the processes where there's enough data for that. But then, so if we summarize all of this, trying to get an overarching picture, now we've taken all three of these greenhouse gases and recalculated them to global warming potential at a 100-year timescale, meaning that what is the effect of these greenhouse gases in the atmosphere? So what's released today, but the effect it has over the coming 100 years, integrated over that time period. You see in the blue, the bottom up, in the pink, top down. And as I mentioned before, we have disagreement for CO2. One says sink, one says neutral. For methane and N2O, they are both sources. So at the end of the day, the global warming potential is a little bit uncertain for at the 100-year time period or 100-year global warming potential. But if we think, but because a lot of the warming comes from methane, actually on the shorter time scales, we are then quite certain that there's already a warming happening. So this is a graph that integrates global warming potential over 20 years. So short-term decadal perspective, 100 years that I showed before, and 500 years, so really long into the future. Because these greenhouse gases behave differently in the atmosphere, they will be there's a difference between looking at decadal timescale to long-term timescale. And if we look at the far right panel there, you see the total greenhouse gas budgets in the bottom up, or anything from quite a strong source of warming at the decadal timescale to a weaker source of warming at the long-term timescale. And if we look at the same for the top-down budgets, again, there's a lot of panels, but just look at the far right, you will see that even the top-down budgets actually show a weak source of warming at the decadal timescale. So that we're quite sure at the decadal timescale, all of our methods is pointed to the Permafrost region already warming the climate. So for the coming decades, it's already actually accelerating warming. And then over very long-term timescales, it might, if the CO2 sink in the forest stays healthy, it might help us cool the climate back down, but that's several hundred years into the future. So that's not really the timescale we're talking about right now. I also want to emphasize that the budget you just saw is from the year 2000 to 2020. So it's a mean over those 20 years. But we've also seen a recent very strong acceleration of the fire cycle in the Boreal zone. Record fire years in 2021 and 2023. You have the references down here if you want to know more. But these 2 years alone, the Boreal forest fires emitted something around 300 to 400 teragrams of carbon. So massive fire years. And then if we take our older budget and just add these fires on top of it, what you get is actually these last few years, a much stronger warming of the climate. And in that case, if you assume, if you take these two fire extreme years, even the bottom up or even the top down models will give us a net warming. So this shows that these disturbance cycles and the variability in disturbances is really important. It makes a big difference to the budget. I actually also want to put it in the context of, this is again from the global carbon budget that was presented here at COP last week. This is a summary graph of changes, so changes from 2023, 2024 in global CO2 emissions. So you'll note that we see the y-axis goes only from 36 gigatons of CO2 up to 37. So this is not at all the full emissions, it's just the changes between years. And we see that China and some other countries increased emissions, Europe and US decreased emissions, but still overall emissions increased by 0.8% between 2023 and 2024. But if adding only the extreme boreal fire years to this, is about that amount. So one extreme boreal fire year really dwarfs the differences between years in emissions. So it's really important to keep this in perspective. Of course, the total human emissions are much, much lower. We're just seeing the top of them. The total human emissions, the bar will go all the way down to the floor or something. But still, these interannual differences in disturbances are critical for the climate and really important to keep track of. And I wanted to emphasize that there are a lot of, so this is work that's already published, so we did it a year ago or so, and now we're still working hard at improving this budget, so we have the new funding coming in from the European Space Agency, CCF, and the CCI projects to work more on Recap 2, working together with CCI plus fire, permafrost and lake projects to get better data and to really try to constrain the differences between these approaches and make some headways in this project. So key findings, some evidence, permafrost region is a net source of warming at the 20 years, neutral at the 100 years, and the sink at longer time scales. Disturbance regimes are really the differences between a net sink and a source. So 5 years, etc., really important. And recent 5 years made the region an even stronger source of warming, but we are still seeing differences between both approaches. And we are still data limited in the science, especially now when we're not getting data out of Russia due to geopolitical tensions. It's making it more and more difficult to really constrain the budgets well. And we also saw that these new approaches, we gathered a really large community of researchers working at different methods. And we're really happy to have new projects that actually bridge between these communities. And I think that we will be able to present much improved budgets in coming years. I mentioned ESA projects. I also want to mention the European Space Agency NASA collaborative project called AMPACT, which is a North American European collaboration project targeting these processes as well. Okay, so that was all I had. Thank you for listening. So I think we had the idea that I will now hand over to the next speaker, and we'll do a sort of Q&A session at the very end. Or otherwise, you can just catch us if you want to have more questions. But now I'll hand the word over to Dr. Jennifer Watts from the Woodwell Climate Research Center.
Thank you, Gustav. So now we're going to focus a little bit more on the issue of methane in high latitudes. And I named this presentation a ticking time bomb. I'll elaborate a little further on why. So atmospheric methane levels are now almost approaching 3 times higher than pre-industrial levels, and they're higher than they've been for at least 800,000 years. And you see 2020 and forward, methane continues to increase quite rapidly. This is really bad news for us because methane has a global warming potential 87 times higher than CO2 over a 20-year time period and about 36 times CO2 over a 100-year time period. That's because of atmospheric chemistry. Okay, bad news. So let's take a step back and think about our global methane emission sources. So quite a bit is from the human sector and solid waste sector, including livestock, waste, landfills, especially rice planting. And then we have about 30% from fossil fuels, oil and gas, geologic seeps, and coal. But a third of global methane is already from wetlands. And we have recognized as scientists tracking global greenhouse gas emissions that rising methane emissions from these global wetlands may quickly undermine our existing climate targets. So what kind of conditions produce methane in general? And this is all natural methane, not just wetlands. First of all, we need microbes present. These are the methanogens. These are archaea. They are everywhere. They're very good at staying in place and waiting for the right conditions to happen. What are the right conditions? Well, we need organic carbon available for the microbes, and we need very wet, oxygen-limited conditions. And we need the surface and the substrate to be unfrozen. When you have all three of these things, we have very quickly the potential to produce methane. That said, not all methane makes it to the atmosphere. We recognize three primary transport pathways for methane. The first is through plants, through the hollow structures and a lot of wetland adapted plants, the eurychema. We also have diffusion. Diffusion is quite slow relative to plant transport. It can be through water or soil. But through diffusion, you actually have a lot of oxidation potential. And then the last emission transport pathway is ebullition, bubbling. This occurs when the methane is supersaturated, and it's a quick transport mechanism to the atmosphere. Typically, we see this happening when there's water. Oxidation happens when we have the methanotrophs in the system, another form of microbes. They love methane. They're adapted to consume methane. And the output of that conversion is to produce CO2. So we go from one form, methane, goes on oxidation, and it still remains a greenhouse gas. So something that we need to consider. We also see a lot of oxidation happening when sphagnum moss is present. It's because the methanotrophs have adapted, and there's a symbiotic relationship with the moss. So if you see a lot of wetlands with moss, we actually don't get a lot of methane happening unless there's supersaturation below and it comes out through bubbling. So the Arctic Boreal zone, the permafrost zone, is a prime place for methane production. It's very wet, it's carbon rich, and it holds over 50% of global wetlands. Unfortunately, it's warming 3 to 4 times faster than elsewhere on Earth. This is a really big problem. Because of this warming, it's becoming less frozen. All the carbon available in the permafrost, more than this twice the amount of currently in the atmosphere, is becoming available for methane production if it remains wet. So what we've seen, what we've heard in the science community, also reflected in popular media, including Popular Science, is the idea, the threat that the Arctic is warming, it's very wet, it holds a lot of carbon. Is this a ticking time bomb for methane that threatens to destroy all our carbon global climate mitigation efforts? So at present, and this is coming out of the Recap 2 papers that were just released in October. At present, based on our current understanding, using in situ observations and modeling, the Arctic boreal wetlands are estimated to be emitting anywhere from 17 to 32 teragrams of carbon per year. And if you think about additional anthropogenic emission sources for high latitudes, that's about 5.3 teragrams of carbon. So those emissions are actually less than the Arctic wetlands. Now, that doesn't seem like a lot, but if we think about that global warming potential, and here we show it over a 100-year time period, that alone is enough from a global warming potential standpoint to offset any uptake, any of that potential gains from the CO2 uptake side. And that's primarily being driven by boreal forests. So it's really important for us to think about methane when we consider this whole carbon equation, because the methane perspective really shifts how we need to pursue aggressive mitigation efforts. This map is the work of a colleague of mine, Xing. Hopefully this paper will be coming out very soon. This is showing our current understanding of the distribution of methane being emitted from the high latitude wetlands. Again, these are model-based estimates, and the distribution is primarily informed by our understanding of where wetlands are as we see them from space. So a lot of wetland mapping goes into this. And I want to point out that mapping wetlands and wet surfaces from space is very difficult. And here we're underestimating, we're not including as part of the equation very small water bodies or wetland areas under forests. So this is likely underrepresenting some of that distribution. And the distribution is changing quite quickly. So we realize that if we're going to keep up with high latitude wetting, we need better sensors in place. That far map on the far right, that shows our current distribution of in situ tower stations that are operating to detect methane. You see in Russia, the Russian Federation, there's currently a gap in information, and so we may be likely underestimating in this region. So given that, how do we actually set ourselves up for success? How do we have the ability to detect a potential methane time bomb? Well, that goes into building a capable detection system where we can rapidly monitor changes and attribute the emission sources across land and offshore permafrost. This requires more strategically placed towers and tall towers and greenhouse gas satellites that are capable of seeing and detecting across seasons, even in the dark Arctic space. And now that we're having more fire emissions and more atmospheric contamination, the atmosphere is actually becoming more wet. That greatly reduces the ability of our passive greenhouse gas satellites to detect methane in these spaces. I think Annette will talk a little bit more about Merlin, which is a greenhouse gas satellite currently in development that's LiDAR based. Right now, we have no capability to see in the dark in the Arctic, and so we're relying on those flux towers. We also need more improvements in our inverse modeling methods and pushing our detection capabilities of existing infrastructure. So that requires a lot of us to really engineer together better systems using what we already have in place. And in the future, we need to think about how do we avoid data latency. If we're going to detect a methane time bomb, we need to be able to do it in near real time. So, reducing the threat of a methane time bomb from high latitudes requires, first of all, global emission reduction efforts. We need to reduce the rapid warming happening in the Arctic. That's the only way. Secondly, we need that methane detection system in place, and we need it now. And the only way we're going to get to both is through public awareness and policy. So I thank you for your attention. And with that, I'm going to pass it over to Elton.
Thank you. As always, great talk by my colleagues, Gustav and Jenny. and that simplifies my talk quite a bit. But before, as always, I'd like to acknowledge that I'm presenting on behalf of the Permafrost Pathway Project, which is a collaborative initiative of the Woodwell Climate Research Center that is dedicated to advanced scientific research and equitable solution to permafrost thaw. And here is, again, in a nutshell, what is the Permafrost Pathway Project is about. We have 4 teams: modeling team, monitoring team, policy team, and the adaptation team. We all work together across multiple boundaries. We're trying to bring knowledge on permafrost thawing, thaw together, and have an integrated approach. And something that my colleagues mentioned earlier, have a better monitoring, have a in-time monitoring, better predictions, reducing the overall gap in observation and modeling. And you've seen this on our previous slides. This is the overall monitoring network that we currently collect data. There is few new stations added in just this year, and they are marked by dark red dots. As it's been mentioned previously, Russia still remains the gap, and we hope that that will change in the near future. So this has also been mentioned, but I would like to reiterate. So we have a better maps and better data sets on methane and CO2. And there's 2 new products that will become available soon. Some of them in review, some of them in preparation. Here's another thing that our team is working on. We're trying to map disturbances, and what we've seen, this so-called retrogressive thaw slumps, it's when your surface gets saturated and then it slides over and basically create an area, exposed area that is susceptible to a faster permafrost thaw. So it's sort of dramatic permafrost thaw. What we're seeing is that these type of features increasing across the circumpolar, and there is a high evidence that the rate of increase of this feature overall, both spatially and rate-wise, is going to continue. And we are doing some work on trying to understand, the spatial extent as well as, the rate. And we're using some AI technique, object recognition AI technique, to quantify the number of these features across the circumpolar. And you've seen this slide as well. I just want to reiterate again what's been said. So one thing when we have just gradual thaw, another thing is when we add the disturbances. Clearly, with adding disturbances, we have our budget is substantially increased. And then if we're talking about 1.5 degrees or 2 degrees, the difference, unfortunately, the scale is not so great, but you can see the difference is almost double for 2 degrees. So with that, I would like to jump in on what our team is doing. And specifically, I'm going to talk about the updates within the modeling team. And we are working on multiple fronts, trying to, again, reduce the bias, improve the modeling part, incorporate observations, and the remote sensing data. So one thing that you need to do when you work with models, you constantly have to recalibrate the model, because the new data comes, then you have to adjust sort of to match your, say, methane fluxes or carbon fluxes. Then you have to build a sort of system that is flexible enough, and that could be you can easily just streamline and plug the data and recalibrate your model. So now it's up to the standard, and it represents the observed fluxes. And that's what we've been working on from the day one. Once I started working on this project, we developed this automated parameter calibration optimization method that is doing that, and it's constantly updating that, making it better. The spatial data assimilation, that is much harder to bring. And for example, the atmospheric science people, they already have it. It's much well developed there. The science is there. For the land system, it is much, much harder because the atmosphere is more or less homogeneous system. The air here is the same as air there. Where in the land, for example, the feature that you have here might not necessarily be the feature that you'll have 10 meters apart. So it's a little bit more complicated. We're working on that. We're implementing that. That requires a lot of new science as well as development, coding, and sort of interdisciplinary expertise. Then we're working on bringing these two major disturbances that we think contribute to a significant extent. And we're focusing so far on bringing wildfires and making sure that wildfires are represented in our model, as well as bringing the thermokarst features. So the thermokarst feature is basically the features that is a part of the abrupt thaw, and they would lead to a higher or faster permafrost degradation, as well as higher emissions from these type of features. And then finally, we are working on a compilation of the 4x4 kilometer resolution data set that the full climatological data set that we'll be using to run both historical simulations as well as future simulations. And for future, I mean specifically we're focusing on this century. And this is just recently, we submitted this paper. It's currently in review. It's basically showing the proof of concept of this calibration technique that we're using in our approach. And this is proof of concept. Then in progress, we already implement that in the bunch of flux tower station sites and sentinel sites in North America. So we're slowly moving to Eurasia. And the goal is to have it by the end of the first half of the next year. But North America is more or less there, so we're working on that publication as well. A little bit on data assimilation. It's a little bit more abstract here. This is more work in the development. We really want to implement this, but it turns out to be a little more challenging than we initially anticipate. But nevertheless, there's a progress on that front. Again, it's pretty conceptual, but just in a nutshell. So we have a model, we have a numerical model that calculates fluxes coming from the thawing permafrost. Then we integrate that model into the so-called the data assimilation system that's already developed. It's a classical data assimilation system. It exists. It's developed by the National Climate and Atmospheric Research Center. And we're using that model. It has all the required features, so we don't have to reinvent the bicycle here. And what we want to bring the both in situ data as well as we want to bring remote sensing data. So that's the ultimate goal. But so far we're testing it at the specific flux tower sites. Just basically, it's a if you will, like one site sort of testing. It's not spatial at the moment. Then the other thing is that, of course, it's the methane production. And for methane production, we have this model that it incorporates both production, evolution, and the diffusion, all the process that requires to account for the methane production from the wetlands as well as from the thermokarst features. Forest fires, we currently have a sort of post-fire model in our terrestrial system model, but we're trying to bring the physical aspect of the model so that we actually can model the fire itself and not rely on external data, on external models that give us this information. The other thing that we've been working on for our model, we have a multiple so-called ecosystem types. Now, what is the ecosystem type? The ecosystem type is basically some area that has a multiple plants. Let's say the certain area has grass, trees, and shrubs, for example, right? So like then we call that a given ecotype, and we have a multiple of these ecotypes in the model, and we've been working on development of the vegetation land cover map that basically accounts for all the ecotypes that we have in the model. It doesn't mean that we're not going to develop more ecotypes, but at this point, we have this many ecotypes, and I don't know from the top of my head, but anyway, there again, like there's for future, we would develop more, but at the moment, it is what it is. And then finally, we are small, relatively small institution in comparison to academia. So one of the things that we've been working on building the infrastructure. So we don't have access to the supercomputers. So what we did, we invested some effort in actually building a supercomputer on the cloud. And we've been successful. Just recently, we've built the high-performance computer on the cloud that will be taking this massive computational assignment, and we are flexible enough. We can run it relatively efficiently, and we can test a bunch of assumptions. So with that, I'm going to conclude. I'm not going to go any further, but this is where we standing at the moment, and in the future, we are well set that by the second half of the 2025, we will have the first circumpolar product, modeling product of the most recent permafrost fluxes. Thank you. The next speaker is Dr. Anat Barch.
Hello. So let's have a look into what we can do with satellite data. It has been mentioned many times already in the previous talks. And yeah, what we can see from space is that the ground is warming in permafrost areas, and specifically along the coastline, it's increasing most. And not only the temperature itself, as we can look at it from this perspective, but also from the perspective of permafrost extent. And this extent, it's shrinking slightly at the so the boundaries smaller. But what you also see on here, we also have the at the same time, the decrease of the ice, of the sea ice, and where the sea ice is decreasing most, that's where we have the highest warming. Yeah, that's where we have these red areas. So this is all linked. So we know these curves of declining sea ice extent, and at the same time, we have an increase of temperatures in the ground. So specifically in years where we see very low sea ice content values of sea ice, we have an increase of warming of the ground of permafrost. Doesn't want any more?
Pointed that direction, probably.
No? There was something. No. Sorry, I cannot. Can you? Yes. And so we have these increasing temperatures in the ground, and also what is at the same time an increase of the thaw depth, the seasonal thaw depth. And actually, we have an increase of 5 centimeters per decade of this seasonal thaw depth. What is means that there's more material available for the microbial decomposition, so more carbon to be released, and it's also a problem for infrastructure stability in communities which live there. We will look at this later in the afternoon at 4 o'clock. Now, this information, the main information here that comes from satellite, what is important for us is land surface temperature observations. And luckily, we have that already for far more than 20 years, 30 years going back in time. So that's what we can use to come up with these time series, in addition to information about what is on the surface, what is the land cover. So that can be used to feed a model and then to come up to gain this knowledge on thawing ground. But there's, what can we learn from satellites specifically about carbon, specifically about methane? So we can look at what is the concentration in the atmosphere, and we can look into what is the wetland distribution, because wetlands, that's where we expect most methane to be emitted. And that then this information goes into these bottom-up and top-down estimates. We have seen many numbers in the previous talks. And specifically, when we talk about the concentration of the atmosphere, a satellite mission, which has been important for the numbers that we have right now, is a Japanese mission, the GOSAT mission, which provides us already for quite some time estimates of methane in the atmosphere. But there are now new missions, European missions, specifically the Copernicus mission, which will give us even better estimates, a much higher detail, and so we can use this information to see where is the wetland emissions, also the anthropogenic emissions, so that the red ones, the green ones, are the ones coming from wetland areas. And so we can look at where is the concentration high, and then also very important, mentioned several times already in these talks, we need to get a good account of where are the wetlands, and here in this case scale is very important. And this new Copernicus missions, they allow us to get them a 10-meter resolution for all the Arctic, and it's very important to have these 10 meters, because if you don't do this, you don't see them. They are because of this really high landscape heterogeneity. So the current numbers that we have, well, they still use the forester information and try to account for this knowledge gap, but we still need to, we are now at the point where we can use satellite data to make these estimates even better, like in the upcoming years. So that's a big chance that we can use here. And then there are, I think we are now at a really interesting time regarding satellite missions. There will be next year, in 2025, a number of really interesting missions being launched from NASA side, from ESA side, which look at all these different things. They look at dynamics at the land surface. So that's really important for these wetlands, but also for what is the concentration in the atmosphere. So 2025, 2026 are really important launches of new satellites here. And one mission, which is actually it's a French-German mission, which is called Merlin, will be launched in 2029. But it's still far ahead. But why is it important? It's important because it is a new technique which is independent from sunlight. And this is what we need for the Arctic. It's really crucial. And that's listed here because it's supported from ESA, also from campaigns and so on. So that is something that we are really looking forward for specifically for the Arctic. Now, all these, so what we didn't really have before, or what we expect to have in the future, are dynamics of wet and dry landscapes. And why is that important? Well, we have permafrost thaw, and we have a change in the wetness of the landscape. And this change, this is something what we need to get right in climate models. And here also the scale matters. So the red dots, it's if you're using a very standard climate model, very coarse, and you do not have this representation of this length of this heterogeneity, this dry and wet gradients. And this means we miss out a lot of evaporation. So now why do I mention evaporation? We are talking about carbon here all the time. But there is, well, you may be aware of the cloud sea ice feedback. And that what relates to climate warming. But there's also a permafrost thaw cloud feedback, which has an impact on temperatures. So if the ground, if it's drying, you have less clouds, you have less albedo, you have higher temperatures. And so we need to get the climate models, we need to get them to represent this. And it's estimated actually that we will have up to even partially more than 1 degree additional warming due to this feedback via this permafrost thaw cloud feedback on top of the greenhouse gases, on top of the carbon. So this is much more complex. So all before we have just been talking about greenhouse gases, but this story also needs to involve the water cycles. And that's where where it's crucial also from the satellite perspective, from these images, to use them to help improve climate models. And that's something that we are working towards too. And thank you for your attention.
Great. Thank you very much to Annette and all of the speakers. So I thought that we could see if there are any questions in the audience or to any of the speakers. Any comments? Follow up? Yeah.
Given that methane is a short and it's active, and global occurs at 80%, what is the long-term impact of the oxidation of CO2 in terms of introduction?
I will repeat the question. So the question was because methane is a stronger greenhouse gas in short time scales, but that doesn't stay that long. So what's the long-term impact of oxidation of methane into CO2? Yeah, I think it's a good question. I think that basically the short-term impact is that oxidation is good at the decadal timescales. But then I think if you start to approach 500 years timescales, it would actually be preferable to have it emitted as methane. I'm not sure exactly where the breaking point is, but it should be on the order of a few hundred years into the future. We'll have a transition. Yes. No.
For chemistry, we all know it's very complicated, accounting for the direct feedback over long term.
Yeah. Yeah. So on the order of a few hundred years, then it will actually, then the warming will be stronger with CO2. Okay, if there are no other questions, thanks to all of you. If you're interested in local impacts, we have a session on at 4 o'clock focusing on that. Thank you.